So exciting. We get to move on to the Poisson distribution. Exercise 13. Emergency patients arrive at a large hospital at the rate of 0.33 patients per minute. That's like a third of a patient per minute. So that's another way of saying 1 every 3 minutes. 0.3, a third of a patient per minute. So every 3 minutes you'd have on a whole patient. All right. On average, 22% of emergency patients are triaged into the most serious category. Okay, so the first part asks, what is the probability of 6 or more arrivals during the next 30 minutes? Okay, the key thing to look for there is the next 30 minutes. So we're going to have to change that alpha that we were given. We were given an alpha of 0.33 patients per minute. We have to change that to a lambda by multiplying that by 30 minutes. So the lambda per 30 minutes here is going to be equal to, as you can see, 30 times B4. 30 times B4 will give you the expected number of patients per half hour or per 30 minutes, which is 9.9. All right. So then we are able to calculate a Poisson distribution. And Poisson is, well, let me just show you real quick how that would look if you were setting it up. There's a probability of 0 patients, of 1, and let's just take this and say edit, where is it? Edit, fill, series, and let's just go from, in the columns, grow from 1 to 20. What the heck? And click OK. There's 1 to 20. Now if I were to calculate, given a lambda of 9.9, which is what we're given, we can calculate equals Poisson dot dist of x, so there's the x, comma, given the mean, there's the mean right there, and I'm going to anchor it, Command T on a Mac, cumulative, false. I just want the individual point, not the cumulative for this point. So you can see it's a very small number. If we average 1 every 3 minutes, the probability that we'll get 0 is very small. I can copy that down and get the numbers. Let's clean it up a little bit. And select all these and put together a insert recommended graph. How about that one? So here's our probability distribution for this particular. Don't hang up on me now. Come on. Don't like to see the spinning rainbow. Okay, so the highest probability here. Notice that by selecting a title here on the second column and the data labels in column G, I was able to get them down here without having to modify manually the data labels on the x-axis. So it looks like the highest probability is for somewhere between 9 and 10. Well, obviously the mean is lambda equals 9.9, so that's what we expected. And the probabilities for all the rest of these, let's change these, Shift Command down arrow, and make them, instead of scientific, let's make them numbers. And let's make them a little bit more, okay, so there's a better idea of the numbers. So the highest percentage is around 12.5%, 12.6, right there between 9 and 10, which is what we expected. So that's what we're looking at for the probability in the first part here. So the first part asks, what is the probability of 6 or more? Now the probability of 6 more, since this thing goes way up to like infinity, to get 6 or more, what you have to do is add up all of the little stacks to the left. So it's 1 minus the probability up to and including 5. So that's how we set up this right here. We said 1 minus Poisson up to 5, given a mean of 9.9 in cell C6, and the true, which would make it cumulative. In other words, it would add up all of those little stacks. And so we've answered part A. There's a 93% chance probability of getting 6 or more arrivals during the next 30 minutes. Part B, what is the probability of 6 or more arrivals during the next 30 minutes that are triaged into the most serious category? Well, the arrival rate of serious patients is 0.0726. How did we get that? It's 22% of the alpha of 0.33. So we take the arrival rate of regular customers or regular patients, which was 0.33, and we multiply that times 0.22, and we arrive at the arrival rate of serious passengers, which is 0.0726. Now, if I want to get the number that arrive in a half-hour period, I have to multiply that times 30. So 30 times C4 gives me the lambda for my calculation of the probability that we get 6 or more arrivals during the next 30 minutes. And once again, that's set up with the same formula. 1 minus Poisson given 5, or up through and including 5, given a lambda of 2.18 and true. So the probability of that happening is very low, 0.02, so about 2%. The next part, C, says if there are 25 patients that arrive in the next hour, what is the chance that more than half of them will be triaged into the most serious category? Okay, this isn't Poisson anymore. Now we're talking binomial. We have a binomial distribution of, because each patient is either serious or they're not. So we have n equals 25 trials, and the chance of success is given to us right here as it's actually, let me give it a little bit more precision, 2.178. So that's the probability of success. So more than half means more than 12, right? More than half would be more than 12. So we calculate that using 1 minus binom dist. Let me put the dot in there so that we're not dealing with a compatibility function. 1 minus binom dist of 12, so up to and including 12, given n equals 25 and given p equals 0.22. True for cumulative, and we get the answer that is, what is that, 0.1%? So this is incredibly unlikely that more than half of the patients would end up going to the serious category for patients. So that's our first little problem in the Poisson distribution.